Thanks.
Good.
Thanks.
So I will talk about an unsolved problem, or actually an unsolved question, at least from my point of view, about generative models, whether it actually makes sense to progress with them, or if we should actually drop them because they are not competitive. And yeah, maybe as a little bit of history, you can see that we are actually living in an era of functional mapping, and actually not since deep learning came, but actually already longer. So the last 20 years were actually dominated, at least in pattern recognition, by support vector machines and now deep learning. And they both just learn functional mappings. Yeah, so you get some input X, let's say an image or some other data, and then you have some functional mapping with some weights that you learn, and then you generate an output, for example, a class label. And that's not even a discriminative probabilistic model. It doesn't have any probabilities here. And in particular, it's not a generative model. That means you cannot sample any inputs X from your model, but it's really just mapping from X to Y. But that has been very, very successful in recent years. That's why everyone is doing that. And in particular, deep learning took over even classical branches of computer vision. I can give you a few examples. So in the past, when I started my PhD, segmentation was still a problem that you didn't do with learning or anything like that. Nowadays, you can do that always with deep learning, and it's pretty flexible. Yeah, so you can segment all sorts of things in medical data, or also in autonomous driving. This is very popular. And in the end, it's all just one network architecture that you train on different data. It learns a functional mapping for your segmentation task, and yeah, you get very good results, and everyone is happy. Or here, that's another problem. Pose estimation was a traditional problem in computer vision, was used. So other methods were used, also generative ones, as I will show later. And now you just solve this as a functional mapping problem, just some training data, and then you can, even from a single image, predict the poses of humans quite well. Depth from single image is another example. So that was something where people would have said 20 years ago, that's a completely ill-posed problem. If you have only a single image, how should you be able to reconstruct depth? You need multiple views for that. And actually that's also true, but of course you can learn just from the patterns that you see in the image, what the depth should be. And meanwhile, we have pretty good results on that. Of course, if you show the point clouds, and you will see that it's not super accurate, but at least the depth maps look reasonable, and at least you get a good ordering, depth ordering in most of the cases. Yeah, and also on actual 3D tasks like 3D tracking, 3D mapping, even there you can actually formulate this as a deep learning problem, which is actually functional mapping from some input variables to output variables. There's a little bit of computer vision know-how in the setup of the architecture maybe, but the main components are actually just functional mappings that have been learned. Okay, so this is all very successful. So the question is, why should we now care about generative models that don't work very well? So you won't find super well working generative models. Most of the papers that you will find nowadays on that will actually be on some toy tasks, and they are actually not on the real world problems like these functional mapping approaches that you see. But one reason why we want to care about generative models is that because actually this functional mapping that we do is going in the wrong direction. Yeah, so it's actually mapping from some measurements, the image, to some semantic data. But actually in the physical world, it's the other way around. So there is the semantics, like the pose, the material of an object, its shape, the lighting, maybe the spatial arrangement of a scene, or sometimes we just put all that together to a class label, and that generates actually the image. So that's actually the physical way on how the image involves, and it's not the other way around, that the image is there and that produces the semantics. That's just what we make up in our tasks. And currently, causal models are a topic that becomes more and more popular, but also just from common sense. there's some feeling that somehow this wrong direction could be an issue. And we also see that in practice. So mapping from the image to the semantics is actually typically anti-causal. And anti-causal mapping has the problem that if you find something out of distribution, then this mapping can lead to anything. Yeah, so you just don't know what to do. So in the best case, and we have already talked about this today already, the best case, you can at least tell that you don't know about this data sample and you shouldn't make any predictions on that. That's the best case. But ideally, we would actually like to also produce an output for this unknown out of distribution data just by generalizing from the knowledge that we have had on other samples. And this is most likely not possible with this anti-causal mapping. Yeah? So for that, you would actually need to go from the physical world to the image and then argue about the semantics in your physical world that would generate that image, and that would allow you to also argue about new arrangements that you haven't seen before. And that's some problem that we also face in practice now. Yeah, so this out of distribution data and out of distribution robustness is a super hot topic, because also companies have found out that when they want to apply their stuff in practice, then they suffer from this out of distribution cases or edge cases, or every company calls it slightly differently. So that's one reason why we want to look into generative models. Another one is this explain away argument. So actually it's also related to out of distribution data. So let's say you observe some scene and you can actually explain many of the things you see in that scene. Then you can explain that away, and then there's some residual that is left over, and that residual is then something new that you haven't observed before. And you can actually start learning about, or putting attention on that, trying to find information about what that is, to actually argue about it. And that's something what humans do. Yeah, so we actually ignore all the things we know and we actually focus on the things that we don't know. And that's only possible if you actually can generate the parts that you know and then basically explain them away, and only then you know what's actually left over. And also that we cannot do with functional mappings. And also from human psychology, there is actually this fast thinking, which corresponds to this pattern recognition that we now practice very much, this functional mapping, which is very fast and very effective, but only works for those samples that we know well. And there's also the slow thinking, where we actually need to think about the thing and argue about it very long. So it's not very efficient in terms of speed. But that way we can actually argue much deeper and can understand things that we otherwise could not handle, with this fast thinking. And it's also not sure if actually animals can do this slow thinking, or if that slow thinking is actually the thing that actually makes us intelligent in a way. And the slow thinking seems to be most related to generative models. So there are some reasons why we would want to care about generative models, but it's not clear if we can do that. Yeah, so here just in the figure again, that this deep network actually is just moving in the opposite direction. Okay, so generative models, of course, are not new. There's a long history of generative models, and actually, if you go further back in history, the more generative they become. So I found here a work from David Lowe from 1987. We did object detection already. So he had a model of a razor blade, and then he could actually, with this model, find razor blades and their pose in an image. That used the generative model. So he has this model, he can actually change the pose and then project them here and see actually with which pose he gets the right projection, and then with that explains the edges that he finds in the image, and then also detect the razor blade. So that's a generative model. I also had some work from my postdoc time where we did human pose estimation, pretty much the same idea. So you have some cameras, you have can do some segmentation there, and then you fit a mesh model of a human into that data, and that way you estimate the pose. Yeah, so that also assumes that you have a model, and then you can generate actually the output, at least approximately, and you make it match with your observations. This, of course, can also be done in a more sophisticated way nowadays. So from Michael Black's group, there are lots of works on human shape estimation. Meanwhile, they are not purely generative anymore, but actually they have many mapping components to detect key points and skeletons and so on. But in the end, there is a shape model with some parameters, and then you try to optimize the parameters to actually match the observation. So that also is a generative model in the end. Or here is a work from Baron and Malik from 2012 for shape from shading, and that's a super good example of a generative model. Yeah, so you observe an image, and then you have these different components: the light direction, the albedo, the shape of the object. And if you optimize all these parameters in the right way, then the combination of those using the rendering rules will actually generate the image. And you can see that in an optimization process, you can then optimize these different components. You get the shape, the albedo, the light direction, the reflectance, and so on, and that generates this image here. But you see, again, it's a generative model. It works very well in this case, but it's a toy problem. Yeah, so if you try that with an arbitrary image, it won't work. The images are too complex for this to work. There are also some generative deep networks nowadays. Well, they are not necessarily generative models in the probabilistic sense, but at least they are generating images. So one main component are convolutional decoders. So it's actually just the opposite of a classifying network, where you start with an image and produce some class label. Here you do it the other way around. So you have maybe some class label, some viewpoint, some other parameters that define the appearance, so some abstract semantics. And then from that, you produce images and segmentation mask here in this case. Yeah, so again, this is actually a mapping. It's a functional mapping, but in this case here, at least in causal direction. Yeah, so you're producing an image using some semantic inputs. And you can also regard this as crudely imitating a graphics engine. Of course, in computer graphics, we can do the same thing, actually much better. You have here all the model parameters, the scene parameters, the light direction, and so on. And if you have all that, then your rendering engine produces a nice looking image from that. Yeah, so that can do that actually much better than the network. Networks have been quite popular because there you can also compute gradients through the network and can actually optimize on those parameters. But actually, there's also inverse rendering these days, so you can differential rendering, so you can also do things there. Yeah, so that's also a hot topic these days. And then there are, of course, the generative adversarial networks. We have seen that in an earlier talk by Anna about GANS. They also use such a convolutional decoder here, but then they have this in an unsupervised learning setting because they don't need actually semantics and the corresponding image as a learning target, but they can learn that just from image sets. Because they have a discriminator using this adversarial framework and can then just learn by using the signal of the discriminator for the generator. We have seen that this can generate very nice looking images. If you use large networks for the generator and you have a lot of data to train from, then these images really look like real images. Another component here is a variational autoencoder. It's kind of a similar or a competitor of GANS, or some recent works have also combined the two. But also here you have unsupervised learning. So again, here's your decoder that actually generates the image from some abstract representation, and the variational autoencoder also employs an encoder that actually maps the image to that representation, and that way you can train this in an unsupervised way. Yeah, so you see also it contains mapping components in the encoder and the decoder, so there's also functional mapping involved. But here you can actually draw samples from that abstract representation and then produce, generate images from that. So that part at least is a generative framework. So now in principle, image analysis with a generative network would work in the way that you flip the direction of the mapping. So instead of a classifier that takes the image and produces then the class label, which is anti-causal, we would basically flip the direction, use a decoder network that from the semantics generates the image, and then retrieve these world parameters here from the physical world via optimization, yeah, so by some differentiation, for example. Yeah, so that would be a generative model, how it would work ideally. Of course, you run here into lots of problems that are largely unsolved. So one problem is that you need a good generator, and the question is whether this generator can really generate new images. Yeah, so Anna has also talked about that this is an issue, and I think we are not super far there. So on first glance, it looks like we can generate new images, but in the end, we can maybe generate slightly new arrangements of textures, but yeah, the recombination of knowledge here is still limited. And the question is if we can make these generators such that they can really recombine this semantic information here in a way that it has never seen combinations of that before. Yeah, but the results still make sense. That is a bit difficult because we have here the curse of dimensionality. Yeah, so these images are super high dimensional. That means doing that directly in the image space will be hard. But where there's some hope is that if you can do a disentanglement into these different components and model each of them separately with a generative model, then this could actually work. Alternatively, you can also use a graphics engine, of course, to generate the images, but then also the question is, where do the models for the graphics model come from? Yeah, so where do we get our shapes from and so on that we want to recombine? And that's also an open question here. And then there's a second problem that comes on top of that. Even if you can generate nice looking images from these components here, then there is still the problem that we already know from 20 years ago, that if you want to do that, then you have to optimize these world parameters, and then you run into the problem of local optima. Yeah, so you can now use your optimization here, but because you have a highly non-convex function, and not like in stochastic gradient descent with deep networks, all the global the optimization issues go away. You will actually run into local optima and will actually not find the right combination here that generate this image. Yeah, so you have this good old optimization problem back. Yeah, these are the unsolved problems here at that point. And so as a summary, in principle, generative models are the way to true intelligence. So this slow thinking, at least that's what I want to claim here. But there are some hard problems on the way. So the curse of dimensionality. So we actually need some disentanglement in some way to deal with that. And also these local optima are hurdles. Yeah, and presumably you need some clever mixing of this generative modeling with mapping components that can reduce your dimensionality or make the problem easier for the generative component. Yeah, that's what I can now put here into discussion, and I'm happy to discuss this with